Because organic molecules often contain many atoms, there are several shorthand methods to simplify their structures. And we're going to look at two of the shorthand representations. We'll start by looking at a condensed structure, and then we'll talk about something called a skeletal structure. So if you think about the word condensed, condensed means to take something out. Like if you had a condensed soup, the water is taken out. Or a condensed conversation means you've shortened the conversation. Condensed structures are very commonly used for chains. Now here's how we're going to condense or shorten it. All atoms are drawn in. Okay, so we're not taking out any atoms, but 2 electron bond lines are omitted. So we're taking out the bond lines. So we're not going to have all the bonds going up and down and side to side. Now, the other thing we're taking out are lone pairs that are on heteroatoms. And remember, a heteroatom is any element that is not carbon or hydrogen. So we're also taking out lone pairs. Now for myself, I'll just start at the left-hand side of the molecule as I go through and condensing it, just moving my way along. And what you always must keep in mind is that carbon atoms have to have the 4 bonds. So here, if we're looking, we have 2 examples. Let's look at this first example, and then we'll try one of our own. So I have a carbon that's right here, and it has 1, 2, 3 hydrogens. So you write a carbon and then an H3. See right here, CH3. Then we go to the second carbon, and it has an H and an H. So you're taking out the bonds. So I write a C, a carbon, and then what's attached to it? CH2. Now notice there's a CH2 and a CH2. There's 2 more. CH2, CH2, and then we get to the last one. You have a carbon, and it has 1, 2, 3 hydrogens attached to it, so we write CH3. So each carbon, you look at the carbon, so I look at the carbon and what's attached to it, and I write it all together. There it is, CH3. Then I see the next carbon, I write down that carbon, it has 2 hydrogens, CH2. This one has 2 and 2 again, CH2, CH2, and then this carbon has 3, and I have CH3. Now, I call this super condensed, but if you notice in this structure, there's 3 CH2s in a row. So the other way to do it is to write the CH3, and instead of writing all 3 of them, you write 1, put it in parentheses, and write the number 3 here. And then here is the CH3. Now the CH3s are on both ends because they're different than the CH2, so you can't include them in there. So let's look at this second example, and I'll change the color. So here I start from the left. Here I have a carbon that has 3 hydrogens. So you write CH3. Remember, we're condensing it, so we're taking out the bond lines. Then here is a CH2 right next to it. So I write the carbon, and it has 2 CHs. Then here's this carbon right here. It has a CH. And since the CH3 is kind of another big thing, sometimes you can keep one of the bond lines. Let me erase this so you can see. So see, in this example, I kept the bond line right there because it made it a little easier to see, and then I condensed the CH3. So sometimes there's a little bit of mixing when you condense a structure. You may keep some of the bond lines if it makes it look clearer. And then finally this last CH3 would be right here, the last one. So again, let's just look at it one more time again together and follow it through. So we're following the carbons. I start with a CH3, and that's this one right here. Then I have a CH2, and that's right here. Then I've chosen to keep this bond line here, so I write CH, and then I can put the bond line, and I do the CH3, which would be right here. And then I finally have one other CH3, which is right here. Now if you notice on this carbon, which is, let me erase this. On this carbon right here, I have an H, but here's a CH3 and here's a CH3. So you can, what I call again, super condense it. So instead of splitting the CH3s, you have the CH, which is right here, and then they put both, there's a CH3 and there's a CH3, both of them attached, so they put a CH3 too. So you can begin to practice and understand how it's condensed, how those carbons written next to, the hydrogens written next to the carbons, their bond lines have been removed, but we understand that they're attached to the carbon that they're next to. Now here's two examples, and we'll try to do these two. The first one says convert it to a condensed structure. So let's follow through. I'm going to look at this first example. So here I have a CH3. Then this is a CH2. And then I'm just going to have an O. Now remember, I'm taking out the bond lines and no lone pairs. That's what's condensed. And then here I have a CH2. And here I have a CH3. Now I'm not going to do any super condensing because, for example, this CH2 and this CH2 are not next to each other. They have an O in between, so I'm not going to put them together. So let's do the second one. So I have a bromine, and I remember I'm not going to write the lone pairs. Then I have a CH2. Then I have a CH2. Then I have a Br. Now I suppose you could super condense and put those two together where you wrote CH2 with, oops, sorry, I'm too close to that button. CH2 with a 2 there, but I'm not thinking that that would be particularly helpful in this case. The idea of condensing your structure is to make it a little more simple, a shorthand representation. So I'm not sure that that would be particularly helpful. Now sometimes, and I know in your homework you might have to do this when you're trying to figure out the shape, you have to put the bonds back. So let's try this. So here I would look here, I'd say CH3. So I know that's a carbon that has 3 hydrogens. Then next to it is a CH2, and then I see though there's actually 4 of them. So there's 1, 2, 3, 4, and then I have an OH. So OH, and the oxygen has 2 bonds and 2 lone pairs, as we learned in a previous video based on the octet rule, so I will add them back. Now let's see about the next one. This looks okay. So here's a CH3 and it says there's 2 of them. So they must both be on that C. So I have a C and I'm going to draw one of them above it. Maybe I won't. Maybe I'm going to draw it below it. And the reason is because I don't have enough room above it. So there's a CH3 and it says I have 2 of them on that carbon. There's another CH3. Then I have the C, which I've already written, and then that C also has another H on it. Then I have a CH2, and my structure, remember they're not attached sideways. Then I have an NH2, so I have N, H, and it wouldn't matter if my H's were above or below. And then nitrogen needs 3 bonds and a lone pair that we learned in an earlier chapter. So hopefully with a little practice, the idea here is not that we're experts at writing the structures, but that oftentimes in medical fields or biological fields, when you have a lot of organic compounds, they'll be written in condensed structures, and it could help you understand what the structure is showing you about the molecule or its formula. Now there is a second type of shorthand notation, and this is called a skeletal structure. And if you think about a skeleton as only having bones, that's really kind of how these structures are. These can be used for rings and for chains, but they actually, I feel like, are most helpful for rings. So what you're going to do is you're going to take out all of the carbons and hydrogens. So remember, carbon is the backbone of these organic molecules, and you're not going to be writing any of them. You won't write any carbons or any hydrogens that are associated with them. So you see here, we're just going to have lines like bones. And every place, we're going to assume that there's a carbon anytime 2 lines come together or at the end of any line. So lines are going to represent carbons. So if you just had a single line like that, it would represent carbons at the end of it. Now, for each line, not only are there carbons, we have enough hydrogens to make carbon have 4 bonds. So in this example, I would also have to understand that there were 3 hydrogens for each one of the carbons to make it have 4 bonds each carbon. Now, carbons and hydrogens are omitted, but the heteroatoms and all of their hydrogens are going to be drawn. So let's look at some examples. So here's an example of a structure. And so if you notice, this has all carbons and hydrogens. This is the skeletal structure. Watch. All it's done is taken, and every time you go from carbon to carbon, you draw a line. And that gives you this. So this right here is a skeletal structure. Now let's reread what we're talking about with the skeletal structure up here, now that you've kind of seen how that one is drawn, how they're connected. So let's reread it so we can really think about it. It says, assume that there is a carbon at the junction of any 2 lines, so where 2 lines meet, and at the end. So I'm assuming in this one there's a carbon, 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 carbon. Then assume for each carbon you have hydrogens to give it 4 bonds. That's where you start getting the hydrogens sticking out, because the hydrogens would be there to make 4 bonds. Now if there were any heteroatoms, they would be drawn in, and in this case there were no heteroatoms. And so let's look at the second one. So if I just tried to imagine, it would be line, 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 line. And if it's a double bond, they're going to draw it. Then I would have O, and then you have to include its hydrogen, H. And this is what you get. So remember, each junction, there is a carbon, and then each carbon has enough hydrogens to give it 4 bonds. Now this is the one that I find the silliest down here, and that is drawing the skeletal structure for lines. So look, watch if I tried to do what I did before and I just drew, connected each one of the carbons, it would look like a straight line. So what they do is they go up and down. So they'll go, let me erase that. So they would go one, and that would be this one. And they do another one, that would be this one. Another one, that would be this one. Another one, that would be this one. And so at each end or junction, we would assume a C, and then we would need hydrogens to go with them in order to give each carbon 4 bonds. Now sometimes you'll notice in your homework they use skeletal structures and condensed structures in the same thing. So really I think organic chemists use the shorthand notation in a way that best represents the molecule, and that could be including both condensed and skeletal structures. So here we have convert the skeletal structure to a complete structure. And the reason I wanted us to do this one is because I know there's a homework problem that wants you to give the shapes, and you have to really be able to make it into a complete structure to do that. So let's try this first one. So starting from this side, I have a carbon that has 3 hydrogens. That's shown as a condensed structure. And then it's attached to a ring. Now what I know is there's a carbon at each one of these junctions. So I have carbon, I'm trying to copy it. My ring doesn't look very ring-like, does it? And then each carbon has to have enough hydrogens to make 4 bonds. So 1, 2, 3, that would need 1. This has 1, 2, that would need 2. 1, 2. This guy's gonna go, so he'll have 1, 2, 3. 1, 2. When you start drawing the complete structure, you realize how nice condensed structures are, or skeletal structures. Okay, that's that part. Now I have a C with an H, and then it has 2 CH3s attached to it. So there's 1. And I guess I'll have to come down here, 2. So this guy makes this. And it's not a beautiful picture, and so it kind of is a sales pitch for skeletal structures, because look at that. But if you're trying to consider the shape, since you need to know the number of atoms and lone pairs around the atoms that it's pointing at, then you'll need to think of it in terms of its complete structure. Well, let me try one more, this bottom one, and let's see if I have enough room to write it. So starting with this side, I have 2 CH3s so attached to my carbon. So I have 1, and then I'll draw another one. This isn't really, I might run out of space. So there's that one, and then I've drawn that carbon, that's the one there, and it has a H, so there's that one. Now I'm going to do a CH2. Now I'm going to do this ring, and so I remember that there's a carbon at each juncture. So 1, 2, 3, 4, 5, 6, and then I'd put the double bonds in. That helps me with carbons. So looking at this one, I have 1, 2, 3, 4. I don't need any hydrogens. This one, oh, let me see, that double bond was really written poorly. It goes there. This carbon has 1, 2, 3. So it'll be 1, 1, 2, 3, 1. That's going to have one coming off. So that's 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4. So you're making sure everything has 4, and on the skeletal structures you add the hydrogens back. Now I have this C, which has an H on it, and a CH3. Sorry, it's kind of crammed down here. Then I come here and I have a C, a double bond O with, and then O, H. So you can see as you go through, skeletal structures really do make a big difference in shorthand notation in terms of looking at it, as long as you know what it's representing.